Okay, welcome to lecture 11, and we're covering unit 2 material now, so higher order ODEs. And so last time in lecture 10 we covered some topics, an introduction to higher order ODEs. So we looked at existence and uniqueness of ODEs, as well as covering something called differential operators, and probably most importantly we looked at this idea of having superposition of solutions. So if we have two solutions which solve an ODE, or multiple solutions that solve an ODE, the linear combination of these solutions is also a solution to that same ODE. Okay, so today we're going to cover some topics that are interrelated to that superposition principle. Okay, and these are: when are this set of solutions to an ODE linearly dependent or independent? We're going to introduce something called the Wronskian and how that relates to something called the fundamental set of solutions. And finally, we're going to construct the general solution to a homogeneous linear nth order ODE. Okay, so let's start with the idea of linear dependence. So this is something that you would be somewhat familiar with in the context of linear algebra, first year linear algebra or linear mathematics. Okay, so usually or at least in the past in linear mathematics, we've studied the idea of linear dependence or linear independence in the context of vectors. So when two vectors are linearly dependent or independent. But in fact, here we're going to write the definition in general for functions. So a set of functions, so f1, f2, f3, all the way through to fn, so this set of all these functions is said to be linearly dependent on an interval I if there exists some constant c1, c2 through to cn. These constants are not all equal to 0. Some can be equal to 0, but not all. But anyway, if there exists some constant such that the linear combination of this set of functions is equal to 0 for every x in the interval. So if I can find some values of c1, c2, c3 through to cn such that this linear combination of these functions is equal to 0, then the set of functions is said to be linearly dependent. Okay. If I can't find any, in fact, if the only solution to this equation is c1, c2 through to cn are all equal to 0, then we say that the set of functions is linearly independent. Okay, and so let's just make a note here that if you have a linearly dependent set, that means that at least one of the functions can be expressed as a linear combination of the remaining functions. So for example, if f1, f2 through to fn, if we showed that these were linearly dependent set, then for example we may be able to write f1 in terms of f2 and f3 and f4. So for example here, if we have the functions f1 equals the exponential of x, f2 equals the exponential of negative 2x, and f3 equals 3 times e to the x minus 2 times e to the minus 2x, well, it's not too hard to show that these are linearly dependent, okay? And that's because I can write f3 here as a superposition or as a linear combination of f1 and f2. Because clearly I can write 3 times e to the x, which is 3 times f1, minus 2 times e to the negative 2x, which is minus 2 times f2, equals f3. Okay, so f3 equals 3f1 minus 2f2. And that is true for any value of x on the real line. So therefore, this set of functions f1, f2, f3, this set of functions is linearly dependent. Okay, well, what about this set? So f1 equals x, f2 equals x squared, and f3 equals 1 plus 2x squared. So we're going to, well, what the example is saying is we're asked to show that the set of functions, the set is linearly independent on the interval negative infinity to infinity. So how can we show this? Well, let's take the opposite approach and say, let's assume that they are linearly dependent, okay, and look for a contradiction in our logic. So if the set is linearly dependent, then we know that we can write the linear combination C1 times F1 plus C2 times F2 plus C3 times F3 equals 0 for some constants C1, C2, and C3. And if I can find some constants that are not all equal to 0, then that would show this was linearly dependent. Or if the only solution to this equation is C1 equals 0, C2 equals 0, C3 equals 0, then we know that this would be a linearly independent set. Okay, so we know what F1, F2, and F3 are, so let's substitute those in. F1 is x, F2 is x squared, and F3 is 1 plus 2x squared. Okay, so now we have C1x plus C2x squared plus C3 1 minus 2x squared equals 0 for all x. So to find the values of C1, C2, and C3, let's try some values of x. Let's just substitute some values of x in there, because this has to be true for all x, right? Because we were asked to be linearly independent on the whole real line. So let's try 3 values of x. What if we use x equals 0? Well, if I do that, I get C1 times 0 is 0, plus C2 times 0 squared is 0, plus C3 times 1 minus 0. So I end up finding that C3 is 0. Okay, not a good start. Not a good start if you think it's linearly dependent, anyway. Very good start if you think it's linearly independent, though. All right, well, let's try the value x is equal to 1. So C1 times 1 plus C2 times 1 squared is still 1, plus C3 times 1 minus 2 times 1, so 1 minus 2 is negative 1, so we get negative C3. But of course C3 is 0, so we just simply get C1 plus C2 equals 0. Okay, so while this isn't killer yet, either C1 and C2 are both equal to 0, or C1 is equal to negative C2. So C1 is equal to negative C2. So let's try another number here. So let's try x equals negative 1. And in this case we get x equals negative 1, so we get negative C1. Negative 1 squared is 1, so we get negative C1 plus C2 equals 0, because C3 is already 0. Okay, but what this tells us is that C1 equals C2. Okay, so we get two expressions here. Well, firstly we get C3 equals 0. Then we get C1 is the negative of C2. But then we get C1 is equal to C2. So the only number that satisfies both of these relations is C1 equals 0, C2 equals 0. All three constants, C1, C2, and C3, are equal to 0. Hence, the set is not linearly dependent. Therefore, the set of functions is linearly independent for any value of x. Okay, so given that we have introduced this concept of linear independence and linear dependence, we would like to know if there's a simpler way to test for this linear dependence. Okay, and the way let's just look at we're going to introduce something called the Wronskian, and this is going to be a way that we can test if a set of functions is linearly independent or dependent. Okay, so this thing called the Wronskian, it's got a kind of a cool name, and I'll show you what it is very shortly. So suppose each of the functions f1, f2, f3 through to fn possesses at least n minus 1 derivatives. Then we can define a determinant, which I'm going to call w, because we're going to call this the Wronskian. So the Wronskian of all these functions f1, f2, f3 through to fn is given by this matrix determinant. So the matrix is made up of the function f1, its derivative, its second derivative, all the way through to its n minus first derivative. Then the next column is f2, f2's derivative, f2's second derivative, all the way down to f2's n minus first derivative. And we continue on in this fashion until we get to the last function, fn, its derivative, its second derivative, all the way through to its n minus first derivative. So we form that matrix, and these vertical lines, if you recall, in matrix algebra, this represents the determinant of that matrix. Okay. So again, these primes denote the derivatives, as we learned in the first week of class, or reminded each other of in the first week of class. And so this determinant is called the Wronskian of this set of functions. Okay, and so we can use this calculation, this Wronskian, this determinant, to determine if a set of functions is linearly independent or not. Okay, so Wronskians and linear dependence. So we're going to calculate a Wronskian soon, so just it'll be a good reminder of how to calculate a determinant of a matrix. So how does this Wronskian relate to the concept of linear dependence? Well, let's take n functions, so y1, y2 through to yn, and these functions are n solutions of the homogeneous, very important that we write here, homogeneous linear nth order ODE on some interval I. The set of solutions is linearly independent on this interval if and only if the Wronskian, the determinant of the matrix, that Wronskian, is non-zero. Okay. So if we have a linearly independent set of solutions, then the Wronskian applied to this set must be non-zero. Okay, so this is like a test. If we have a set of solutions, if we want to know if they're linearly independent or not, we're going to take the Wronskian of the set. Okay, and similarly we can make one more definition, which is called the fundamental set of solutions. Okay, and that is said any set y1, y2 through to yn of n linearly independent solutions to the homogeneous linear nth order ODE is said to be a fundamental set of solutions. Notice here that the ODE we're trying to solve is nth order. And notice here we have a set of n solutions. Okay, so to get a fundamental set of solutions we need two things. Okay, a fundamental set of solutions needs n solutions, and those n solutions need to be linearly independent. Okay, they need to be linearly independent. If that's true, if we have n solutions and they of the nth order ODE and they are linearly independent, then we have what's called a fundamental set of solutions. Okay, if we have a set of n solutions to the nth order linear homogeneous ODE, we can check if they are linearly independent by calculating the Wronskian of this set of solutions. Okay, if they are linearly independent, they form a fundamental set of solutions to the ODE. And just as a bit of theory that we're not going to prove in this class, the existence of a fundamental set of solutions to the homogeneous linear nth order ODE is guaranteed to exist by the existence and uniqueness theorem. Okay, so given a homogeneous linear nth order ODE, we're guaranteed to have a fundamental set of solutions which are linearly independent from one another, and we can check that linear independence by calculating the Wronskian of the set of solutions. Okay, why do we care about finding a fundamental set of solutions? Well, the reason is we have one more definition before we look at some examples. If we have a fundamental set of solutions, so we've been given n solutions to some linear nth order homogeneous ODE. We've tested using the Wronskian that they are linearly independent and therefore a fundamental set. So given that we have a fundamental set of solutions to the homogeneous linear nth order ODE, then the general solution of the ODE is the linear combination of this set. Okay, so the general solution y to the homogeneous ODE, in fact the homogeneous nth order ODE, and also linear, is y is equal to c1 times y1, the first solution, plus c2 y2 plus c3 y3, all the way up to cn yn. And by the superposition principle, this general solution is guaranteed to solve the ODE, the original ODE. Okay. Again, Ci, C1, C2, and so on are just constants. So the point is we need a fundamental set to form this general solution. Okay. So let's look at an example. So I haven't told you how we're going to solve these higher order ODEs yet, but we're going to learn that as the class goes on. But for now, I'm just going to say, given that y1 equals x, y2 equals x squared, and y3 equals 1 over x, are three solutions to the ODE, x cubed, the third derivative of y, plus x squared, second derivative of y, minus 2x times the derivative of y, plus 2y equals 0. We're asked to find the general solution. Okay. So again, we are told that each of these y1, y2, and y3, each of these solve this ODE. Okay. So you can check that. You can calculate the first, second, and third derivatives of each of these functions individually, and substitute them into the ODE, and you'll find that the left-hand side always equals 0. Okay, so we have a set of solutions, and in a third order ODE, three solutions. These three solutions are a candidate set for our fundamental set of solutions. But firstly, we need to check if this set y1, y2, and y3 are truly linearly independent. So like I said, the three functions are solutions to the ODE, but do they form a fundamental set? We need to check if they are linearly independent set, and for that, to check that if they are linearly independent, we must calculate the Wronskian of the set of functions. Okay, so the Wronskian again consists of this matrix with the functions y1, y2, and y3 in the first row. In the second row of the matrix, we calculate the derivative of each of these functions. So the derivative of x is 1, of x squared is 2x, and of 1 over x is minus 1 over x squared. And then finally, because we need a square matrix, we need to calculate the next derivative, which of course the derivative of 1 is 0, the derivative of 2x is 2, and the derivative of minus 1 over x squared is 2 over x cubed. So this matrix we've just formed, we calculate its determinant, and that is defined to be the Wronskian. Okay, well, from first year linear mathematics, we know how to find the determinant of a matrix, of a 3x3 matrix. So the first thing we'll do is we'll circle the upper left entry here, and then calculate the determinant of this lower matrix in the green square. Okay, well, what is that? Well, okay, I can write this as x times this determinant of this smaller matrix. Take away 1 times the determinant of the matrix formed by these 4 entries in purple here. So take away minus 1 times this matrix x squared 1 over x to 2 over x cubed, plus 0 times this matrix up here. So of course, one nice thing about this is that we're multiplying by 0, so of course we're not going to have any other terms here. Okay, well, we know how to take the determinant of 2 by 2 matrices quite easily. We cross multiply the diagonal terms, and we subtract the product of the off diagonal terms. Okay, so if we do that, we get x times 2x times 2 over x cubed, which is 4x over x cubed, minus negative 1 over x squared over 2, so plus 2 over x squared. The second term here, we take away 1 times x squared over 2 over x cubed, so 2x squared over x cubed. take away 1 over x times 2, so minus 2 over x, which of course we can simplify. We get 4 over, we multiply through by x here, so we get 4 over x plus 2 over x minus 2 over x plus 2 over x. Okay. Well, if I do that, I get 4 plus 2 is 6, minus 2 is 4, plus 2 is 6. So I get 6 over x. Okay. And of course 6 over x is greater than 0 for x greater than 0, and in fact, yeah, x greater than 0 here, so we're not looking at the case where x is equal to 0, thankfully. Otherwise we would have, well, something going to infinity, but the point is it's not equal to 0. It's not equal to 0. So therefore, this set of functions, y1, y2, and y3, by this Wronskian test, is linearly independent. Okay, so this set of functions is linearly independent, and so therefore this set of functions, y1, y2, y3, is a fundamental set of solutions, okay, to the ODE. Since this is a fundamental set of solutions, I can write the general solution to this ODE like so. I'm using a capital Y here. It doesn't really matter whether you use a capital or a lower, but the general solution is c1 times x plus c2 times x squared plus c3 divided by x. So the linear combination of y1, y2, and y3. And again, the interval is defined to be x greater than 0. The key point here really is, in nth order ODE, you have n solutions. If those n solutions are linearly independent, which we can test by calculating the Wronskian and making sure it's not equal to 0, then that set of solutions is a fundamental set of solutions. If you have a fundamental set of solutions, you can form the general solution by taking the linear combination of that fundamental set of solutions. And by the superposition principle from last class, this general solution is guaranteed to satisfy the original ODE for any real values of C1, C2, and C3. Okay. Good. So we're almost through for class today, but I just wanted to summarize everything that we've written. And so now I'm going to write this in terms of this linear differential operator that we learned about last time. So this linear differential operator, we can write like so: some constant times the nth derivative plus some constant or function of x or constant times the n minus first derivative, all the way through to the a1, so some function or constant multiplied by the derivative plus some function of x. For the homogeneous differential equation, so where the right hand side is equal to 0, okay, we're only dealing with the homogeneous case here. We'll deal with the non-homogeneous case another day. If y1, y2 through to yn is a set of solutions to the nth order homogeneous linear ODE, really pointing out here that you have to have n solutions to this nth order ODE. And if the Wronskian of that set, the Wronskian of y1, y2 through to yn, is not equal to 0 for all x in the interval, then the set y1, y2 through to yn is linearly independent. If the set is linearly independent, then it is a fundamental set of solutions, and the general solution to the ODE can be written as follows. Okay, I hope that's clear, and if you have any questions, please feel free to post on the student forums or get in contact with me directly. Thank you for your time today, and I'll see you in the next class.